Bob Bosworth here. Welcome to Gas Tungsten Arc Welding Basic Processes Defined. The next little while, we're going to cover off a whole bunch of information when it comes to basic tungsten arc welding with respect to direct current operation. Now, this is something that's very specific for tool steel, stainless steels, and regular steels when it comes to getting high quality processes. Now, what's going to get covered today is the general welding safety aspect of every program that I do, and the gas tungsten arc welding process and equipment. We need to set this equipment up. We need to understand what it is and how it works to work properly. Now, welding safety review. I always start by talking a little bit about breathing air because I'm going to make reference to oxygen, which represents 21% of our atmosphere, nitrogen, which makes up 78% of our atmosphere, and of course, argon, which makes up the shielding gas for what we're about to do. The argon itself is pure. We don't need to add anything else to it to have the TIG process. That's why they refer to it as a tungsten inert gas process. Now, for some specialty welding, they actually do dope argon with small amounts of other gases, but by and large, argon is pretty much pure, and its very close counterpart is helium. But we try not to use helium wherever we can because helium has its own level of problems, including sometimes being in very short supply. Ventilation for tool steels has to be considered now, because if we're doing any tool steel work, we have to remember that we're working with something that has a high amount of chrome for the hardness, has a high amount of manganese, and of course, we're always using, as we've discussed, argon gas as our shield. Argon is one of the inerts. It's not going to poison you. Argon, neon, xenon, radon, and krypton are the 6 known inert gases that you find on column 18 of the periodic table. Now, these are naturally occurring. They're all over the place. Radon happens to be the heaviest gas, being 8 times heavier than air. If you took a breath of radon, you couldn't even blow it out. It's so heavy. Now, argon gas is very much in supply because we have lots of it. And I'll explain why we have lots of argon. Anywhere where you're making steel, you're actually getting argon at the same time. And I'll explain a little bit later. Now, chrome and manganese are something you don't want to be breathing, and there's always fume. Where there's welding, there's fume. There's enough heat at 11,000 degrees, and that's what the plasma is coming off the end of your TIG torch. And there's enough heat in there to actually get everything to the point of almost boil. So there's fume that gets released from the process. This is something we don't want to be breathing, and welding in confined spaces should always be avoided until you have proper ventilation. Just think about the position that you're in and what you're doing and what the confinement is around you when you're doing welding. And remember, if they're blowing a fan on you, don't be blowing it on the weld because you're going to cause all kinds of issues. Now, welding helmets themselves always have to be considered, especially with the new welding helmets. New welding helmets, of course, and it's not so new to have auto darken, but auto darken have come down in price to the point where anybody could be using it. Now, the part I want to talk about in this particular table is the gas tungsten arc welding. So gas tungsten arc welding, they've got it defined in here as less than 150 amp. Your minimum shade is 8 and your max and your suggested is 10. And you could still use a minimum from 150 to 500 as an 8 with a maximum of a 12. What this tells you is a minimum shade, scientifically, this has been tested, that you're not going to get ultraviolet damage to your eye. Consistent ultraviolet damage to your eye is going to cause cataracts when you get a little bit older because your eye is trying to defend itself. It's literally putting on a little bit of a callus to try to protect itself from all these UVs. Now, gas tungsten arc welding will burn you, and it'll burn you because there's no smoke or no reason why. If the arc rays reach you, you're not going to get somehow burned. But notice that there's a difference in what the darknesses are and where we end up running. I used to use micro TIG, and when I moved into micro TIG, we were welding less than 10 amps. You were welding with a filler material that's as big as a hair, 5 thou maximum, and you would slide this down a tube, and that's how you would introduce it to your welding process. So you can do a lot of cool things with gas tungsten, and we have to respect the fact that these arc rays are going to be very strong, and we always have to respect whatever you happen to be welding and that base metal. We always have to make sure we got our ground clamps in a good position, and with this process, I always tell people that I prefer this type of a ground clamp, the ground clamps that have a spring on them. And I do that because if a person ends up with an electric shock, and if you're going to get a shock, you're going to get a shock off this process. The high frequency in it likes to jump between one point and another, and absolutely loves it when you get sweaty. And I've seen many people get a pretty bad shock. If you have this type of a ground clamp on, I can grab it and I can pull it off for safety. And I always keep that ground clamp within a step away from you. And then there's this type of ground clamp that you could be pulling on it all day long, and it's not going to do anything, because when you get that electric shock, and I've had a few of them, all your muscles clench. So if you're holding on to the gun and you're using a finger control or something like that, there could be a danger here that you're literally locked on. This, of course, is a serious problem with shielded metal arc welding, stick welding, because as soon as you put the stick in it, it's on, it's live. There's no way to get off of it. So I got a couple of exercises I want to talk about with tool steel. And these are things we're going to do later. And I'm putting these on now because I want to talk about these exercises as I'm going through and talking about the process itself. And I'll talk about specific exercises and how they get applied. So first off, we have two basic parts to a weld. We have one which is dimension and structure. How big is the weld? And with tool steel, we have a new challenge. Are we going to be joining, or are we going to be hard facing? If we're joining, we're using a completely different alloy and different material than if we're hard facing, where our goal is to make the surface as hard as we can because we have tool steel working steel. This is steel that's so hard that it could actually start working with steel. Next, the penetration and metallurgy. Penetration's up to you with TIG welding. If you know what you're doing, you can look and see if you've got a liquefaction of base metal. Once you do, you can go ahead and start adding filler material. You are in control of when that happens. From a metallurgy point of view, if we're talking about tool steel, the whole thing relates to what goes on down here. You have to know your base metals. We have to know if this is D2, O1, A2. We've got all these different types of materials, and we have to know which one it is to make our electrode, or I shouldn't say electrode, but in this case, to make our filler metal selection. So there's more to it than just knowing. You have to do a little bit of homework. Most die shops have organized their dies and actually identify them and number them in such a way that they can actually go back and say, well, we know what this one is. We know this material is. We know it's not cast iron. We know it's A1 or A2 or O1. We know whatever it is. A quick word about the parts of a fillet, because I'm going to start throwing these terms out here pretty soon. So here's your typical fillet weld, and these represent the toes of the weld, the point where base metal and weld metal meet. They tell us where these materials fuse together and how they fuse together, and whether the two materials were hot and whether the material has a smooth transition. Or can I see gaps in here? Can I see gaps that give us problems? And to think that the material doesn't have any fusion from the base metal. Again, TIG welding gives us so many advantages to seeing exactly what we see, but you have to recognize those to make it real. There's the face of the weld, the part you can see, looking for porosity and so forth. The theoretical throat is the size of this weld. Not as big a deal for you guys when it comes to the size of a weld. Professional welding people that weld every day weld to certain sizes. You guys don't have to worry about that as much as meeting your goals for the amount of fill you have. The effective throat adds the thickness, or the depth of penetration. The next is the most common for the maintenance application, where you've got the vertical leg and the horizontal leg. These are the typical weld sizes you would get if you were making components, any of the components on the shop floor. Lastly, the reinforcement. The reinforcement represents the bump of the weld on top, and that is how far does it stick up. If this gets too big, it starts to cause issues. It actually starts to cause distortion issues and crush issues, where this material is trying to pull on itself when the welds get too big. Multiple layers of thin passes is exactly what the order of the day is for TIG welding. So just a couple of more examples here when we're talking about our multi-pass welding. Our multi-pass welding represents building it up to the point where we can take it back to a machine and likely repair it. And that is, you might have to machine some of this out. But notice how I've done my multiple passes here. The first pass represents covering off everything inside the fillet corner. The next one represents an extension of the filler, extension of the leg. So we've gone out further, and the center of this weld is actually the edge or the toe of the weld underneath it. Same up here. This layering makes sure that we get an even compensation for penetration. And it has to balance out. The deepest penetration area for your weld is usually the throat. So the outside edges don't penetrate as much. So going over your toes is important for each pass. I'm going to demonstrate this one as well. This is one of my favorites because it teaches a lot if you can do that well. We, of course, have our other layers where we're putting materials in place and putting our passes in, and they're half overlaps that are being put in. Now, these half overlaps need to be put in quickly and smoothly and with as much care as possible to make sure that there's actual liquefaction. Now, some of these welding processes require us to travel a little bit faster. And we also have to respect something called inner pass temperature. Now, I'm going to talk about this later, but this is the perfect time to talk about it. When you have an inner pass temperature, it just means you can't take this welding, this big piece of plate that we're going to do, and you're going to do this one for me. And if you can't take this plate and just start putting pass after pass after pass on it. You have to respect the heat input for the plate, and we're going to respect something called inner pass temperature, which we will talk about again when we get to the metallurgical side of the course, which is in part 2. This is one of my favorite things to do because it actually puts us in a position where we get to learn how these passes go into place and the layering that we need to do to get the strength we want. So when I have this particular program, or running this particular program and putting these layers in place, I'm also watching the temperature. Now there's a section coming up on the metallurgical side that defines what we need to do that. Order and edge restoration is common when you get edges that break. Notice I'm welding to that corner and then I move to the other corner and I'm coming back and I'm closing the weld by overlapping craters, the very last bit of the weld. Now when that happens, it should be rolling over these edges just a little bit to give me whatever buildup I need on this surface or give me whatever repair I need from this edge. Chip repairs, if there was a chip or a piece missing or a gouge out of this material right here, you never just put a little bit of weld right there. You'll find that the edges of your weld, the sharp side, the sharp edge, will start to get melted away. So we weld towards it, and then we weld away from it. Whoops, sorry. And then we weld away from it. We create a little hook here. And I do these in slowly just so you can see the pattern that I'm using. And in this way, these little areas right in here where you welded to the edge and then away from the edge will sharpen. And they'll go very sharp, and you won't have to flip it around. You won't have to put more weld on the bottom or anything like that. So tool steel equipment power sources. There's nothing more basic than tool steel, than TIG welding tool steel. It uses a constant current power source. We weld in DC straight polarity. Now I've left a couple things options open here for us in tool steel. Shielded metal, which I might want to use. I might have mentioned I'm a big fan of using shielded metal stick electrode for joining because it gets a lot of material down in a hurry. It takes forever to get the shielded metal with no advantage if you wanted to try to take the softer material, is the underlay material, or what we know as the joining material, which is usually high in nickel. Gas tungsten is our goal, and we run it in direct current electrode negative, also known as straight polarity. So this is our equipment, and we're going to work our way to it here by starting off with the very basics. Our high pressure cylinder, we know that this is going to be argon. So our shielding gas, being argon, has a shielding gas flow meter. We have control over this gas, the way this gas is flowing. So the shielding gas flow meter is usually set somewhere between 20 and 25 cubic feet per hour for a small amount of weld like you do. There's a hose that runs, of course, to the gun. We have a power source set on DC. Notice it's a constant current power source. We know that because we are setting our current in amperage. This is not like a TIG welder, or sorry, not like a MIG welder that runs as a constant voltage. We set voltage and wire feed speed, and current is an outcome of it. Completely different class for a different time, but much different. We have an earth grounding going on. Then, of course, we have our lead cable and our ground cables. And then we have our TIG torch. Now, this is a pretty typical TIG torch. This is from a company years ago that developed a torch called Weldcraft. Pretty much everybody on the market has stolen this design and these parts just because there was no need to reinvent the wheel. This one happens to be just what we'll call gas cooled. There's no, even though you'll see it in advertisements, there's no such thing as air cooled. Gas cooled means that it utilizes the gas running through the torch to help to keep it cool, and it needs it. And that's one of the reasons why we got to make sure we have the shielding gas flowing properly. If we don't, it will begin to overheat, and it will overheat drastically. But this is a typical setup with our lead cable and our ground cable and everything being the way it is. You could go to Canadian Tire right now and you could buy a welding machine for $300, Princess Auto, and you could plug it in. As long as it's direct current, you could TIG weld with it by different methods. You could scratch start it. You got to put a TIG torch on it, shielding gas. Other than that, you could scratch start it and you could TIG weld all day long. It's the process I like to have around the house. I got a shop that's well equipped, but I still, if I'm going to do a little bit of something around the house, I always like to have my little TIG torch around because I can make a few things for some of the stuff that I get involved with. This is your typical torch. In this particular picture is your liquid cool version. There's a couple of interesting things about this I want to bring up. So first off, there's the nozzle. Now people call this nozzle ceramic. It's not. It's made of a material called alumina, which is like an aluminum oxide. Think of this as like a very fine grinding wheel. Very fine, the same material we make a grinding wheel. Vitrified aluminum oxide is what these are made out of. And they will melt. If you use a nozzle that's too small and use a lot of current, you'll actually see the edges of the TIG welder start to melt and liquefy. But the material here, we're looking at about 8,000 degrees to get it to melt. So that's quite high. The tungsten electrode, which is not consumable, it does not belong in the weld, nor should it be. But if you use a tungsten that's too small for what the job should be, that tungsten will get liquefied and will drip into your puddle and cause you a world of hurt. So you got to make sure that the tungsten itself stays intact, and you got to watch that the tungsten's never loose. If you're TIG welding and you look down at your tungsten in the TIG, and it's jiggling on the end of the electrode, your tungsten is too small for the current you're running, and it needs to get bigger because it should be able to overcome. It's being overcome by all the heat. Tungsten, much like tungsten, like aluminum oxide, melts in the 8,000 degree range, 7,000 to 8,000 degrees. We'll talk about this in metallurgy, but when it gets to those stages, you got to make sure it's big enough so it won't drop away. The collet body is one of the important things. I will be going through the collet body and the assembly of this section with everyone that goes through the program. As soon as we do that, you're going to understand a little bit because there's a sequence for putting these together. One of the things you always remember is the collet body itself. Collet body goes in first. And you always check your collet body to make sure your collet body and your collet are the correct size. This is a match. If this is 3/32, this is 3/32. They have to be a match, or you'll have problems keeping your tungsten tight. This piece of copper collet here surrounds the tungsten and applies pressure to the outside of it, and it's all copper. The more surface area it touches of the tungsten, the more it can assist in drawing heat away from the tungsten and trying to keep it cool. It works very efficiently when we're running a liquid cooled torch. This particular torch body runs coolant to the torch through one tube, and then it runs it to the torch. It does a loop around and comes back, and this is the power cable. Plus, it has the coolant returning right around. It's actually the cable's loose inside this pipe or this tube, and it's being loose in there to allow the coolant to return and circulate around and through this pipe and keep that cable nice and cool. Now, they've made that cable nice and cool, nice and small, just so you can handle it better. But this just also means you have to have it flowing. It has to be flowing, that water, or this thing will just burn right up. And of course, we have to get shielding gas to the torch. So we've already talked about this, but you folks should be setting up, or we're going to be setting up for your TIG welding in direct current straight polarity. In direct current straight polarity, that's an old term, maybe an older term at this point, to say direct current electrode negative. Now look at the direction, look at the video. Look at the direction that is flowing. And that's actually correct. The electrode with the electrode negative, the electrons are flowing to the plate. When the electrode becomes positive, the electrons have to come off the plate and come up and make it back to the tungsten. You will see this in aluminum welding. In aluminum welding, there's electrode negative and then there's electrode positive. And this is a cycle that just keeps bouncing back and forth that we can control. Aluminum welding, whole different course for a whole different time, but this would be a good prerequisite. So let me know if you ever want to do anything like that. Now, a quick word on balance of heat. When you're welding a straight polarity electrode negative, this is what we're looking at. So 1/3 of the heat's in the tungsten, and 2/3 of the heat is actually in the plate. Now, this is perfect for our TIG welding. It doesn't matter if we're talking about tool steel or copper or anything like that. This is perfect because our base metal needs the heat, not our tungsten. In fact, our tungsten in straight polarity or electrode negative is sharpened. This sharpened tungsten helps us out quite a bit when it comes to keeping a smooth column, a smooth and controlled column of plasma right here. Now, this one in the middle just isn't done. This one in the back is done for aluminum. This is exactly what's done for aluminum, whereby there's a switching. So there's a switching for alternating currents. So there's a time when this is positive and this is negative, and this is negative and this is positive. So it's flipping back and forth. So there's a balance of heat. Don't get confused between what it should be, because you should always have AC for aluminum and some of the very thinner materials. AC works much better. But for your tool steels, you're in direct current straight polarity or direct current electrode negative. Now, a quick word on that liquid cooled torch again, because I want to reiterate something. So what they do is, to make the torches lighter for us for liquid cool, they actually take this big cable, and if this was a 250 amp cable, it's a big heavy thing. And if you've done any stick welding, you know how heavy the cables get because it's a big chunk of cable. But if you pick up your TIG torch that's the same 250 amp or 250 amp, you'll notice it's way lighter. That's because they circulate the water, the coolant, back from the torch, and they circulate it and it runs back to the cooler around a smaller cable. Here's the problem with this. If this water is interrupted at all, this cable gets hot fast, and it gets hot fast, and it just starts everything burning and melting, and the water starts coming out, and then the arcing starts to happen as a result of the short circuit because the water is everywhere. It's kind of a problem. So you have to be cautious of that. So the key feature, what I'm trying to get at, you have to make sure that your cooler is working properly. You have to make sure that the motor's working, the pump is working properly, and things are getting circulated in order to get it nice and cool and to keep your torch under control and make sure it's flowing. If this coolant is influenced to stop or anything, it has a bit of a blockage, you're going to be in trouble. If you wanted any more details on what that coolant should be, contact me, and I'll get you set up with some more information on that. Now we have rheostat control, of course. This is important for TIG welding, and it's especially important for us us people that are starting to play around with some tool steel. So if we're starting to do some tool steel, we want to use a foot control because we have to change our current when we're close to an edge, but we might want to give us more current when we actually get away from the edge and get more to the body of the material. You need to be in control of this for a bunch of different reasons. One of the exercises I'm going to give you is a crater control exercise where you're going to just start welds and you're going to just end welds right there on the same spot, and you're going to make little tiny pyramids of material. This is to check and see if you know how to fill a crater continuously without stalling the arc, because we want to get the arc established and then we want the arc to shrink as we go. And these are things we can do. Okay, so foot pedal is one thing, hand control is another. Now, I am a big fan of hand controls because I don't have to use my foot. If I got to crawl inside something, I want to have a hand control available. If I've got two of them sitting there, I don't care which one I have. Tool steel, if it's a foot pedal, I'm fine. If it's a hand control, I'm fine. But if you have a preference, if you wanted to go with a hand control or learn some hand control stuff, that's always an option. And if you let me know, I might actually have one with me when I come to your plant to do practicals. So the gas tungsten arc welding process is right in front of us now. So we have a tungsten, we have a nozzle, we have a filler material, we have an arc, we have a plasma cone, we have a tungsten electrode that actually is in electrode negative, so it is able to hold this point. If you were in the wrong type of current, if you were in AC or something like this, the sharpened tungsten, which we'll define a little bit later how your tungsten should be sharpened, that sharpened tungsten wouldn't last for 2 minutes, and you'd be having to resharpen it. There's the molten weld puddle that's going on back here, and the objective is to take this puddle and to start to liquefy the base metal, and then at an appointed time when you see there's enough liquefaction going on, then you take this filler rod and you bring it in and you touch it to the liquefied surface. This rod never leaves this shielding gas, and you can't see the shielding gas. This is one of the trickiest parts about the practical. So you have to keep the filler material inside of this gas shield even though you can't see it. But that being said, it's pretty simple to see where it is. You can see where the nozzle is, and you can see right below it, there's always going to be a flood of material. A few words about shielding gas. So there's 7 purposes for having shielding gases, and they have effects on the welds. And let's see what they do for a minute. Now, temperature control. As the gas flows through, and by the way, this is the same thing I could give you for MIG and gas metal. If you don't have a liquid cooler on your gun, it's not really air cooled, even though they call it air cooled. We're counting on shielding gas flowing through this and keeping the tungsten or the diffuser, contact tip, all this stuff nice and cool. So making sure you have the proper amount of shielding gas flow has a lot to do with the temperature. If you wanted to look at this for yourself, I have FLIR camera equipment we can set up, and you can see an enormous difference between the flow rates to try to keep contact tip life where it's supposed to be. Displacement of air. Air is no good. The 78% nitrogen alone is a problem, but the 21% oxygen is even more of a problem. So all these things tend to contaminate the weld and give us problems. We need our inert atmosphere. That is inert being. It does not combine with anything else to create any new compounds, so it's not going to affect the base metal. We need to protect the base metal. We need to protect the weld deposit. We need to protect the cooling weld metal behind the puddle. There's always a liquid area behind the weld puddle. If that's not protected, it's going to oxidize, and it's going to oxidize badly. In welding steel, if this happened to be a MIG program, you can actually add gases to this that modify the type of weld you get. If we're welding with steel, you can actually, and you can't TIG weld with carbon dioxide, but if you were MIG welding, you added carbon dioxide to your gas mix, you could actually toughen the weld slightly with carbon content from the carbon dioxide. And of course, creation of arc plasma. The creation of arc plasma is the key for it all. We have to create the right environment to have this work. So we have our flow control. Our flow control has to do with having graduations for whatever we should be. So I think for the size of tungsten, for your typical tool steel program, 20 to 25 cubic feet per hour is more than enough flow to get what we want. Remember, too much is a problem. Now this is there's a little ball inside here and it's going to go up and down, and we're going to validate that pressure. And I have a little exercise that I do when I do practical to talk to you about these flows and what we need to consider. Now, I borrowed this from the MIG welding world in showing how the mixed gases affect the welding penetration zones and the welds based on their mixes. Pure inert, pure inert, pure inert mix. And this is what we commonly do, and what you guys are commonly doing on the shop floor when you're making parts. That's argon and carbon dioxide. Most plants are 90-10. I have tuned up a lot of these for 90-10. I'm sure that most companies are about 90-10. 85-15 is still very common though. Carbon dioxide, there's a lot of plants that decide they're going to use straight carbon dioxide for the welding process. It's a little surprising, but given certain welding equipment, you can weld with straight CO2 very well, and straight CO2 is 1/10 of the cost of regular argon. A few words about the tungsten electrodes. The tungsten electrodes, and I wanted to put this in here, we're talking about a welding arc now when it comes to the temperature of things. Here's where tungsten melts. Tungsten melts at about 6170 Fahrenheit. So tungsten itself can be welded. I had a job in power generation years ago where we commonly welded tungsten materials. It's a little tricky, but relatively easy once you understand that it doesn't want to melt. We need an enormous amount of heat. We're using special mixtures of gases to try to bring the heat up to create some efficiency, or you're doing it very, very slow. Different types of tungstens. Your tungsten you're going to be using, there's a couple of different options actually. Now, this is your pretty standard 2% thoriated. There's 1% thoriated. There's lanthanated. And then we have ceriated and lanthanated. Ceriated is the blue, and these two are actually known. I've seen these two packaged as lanthanated. Now, these are used for basic ferrous materials on standard equipment. Now, normally, if you're welding aluminum or something like that, we end up with non-ferrous, we end up using something called a pure tungsten. New technology machines, for example, the Miller Dynasty, the Fronius have a couple of different versions of the magic weld, and they do a very good job with a 2% thoriated on aluminum, or a ceriated or lanthanated on aluminum. There's a bunch of different options here to use. I'm going to make this point right now, and I'll make it as clean as I can. I've worked in many shops and worked in a lot of different places, and everywhere I go, I take lanthanated black, and I replace everything in the shop with just lanthanated, because I can and have proved that I can do absolutely everything with a black lanthanated tungsten, and that is I could use it on AC, on a conventional machine, where I can have put a nice little ball on the end of it like I want. I could use it on AC with an inverter that requires higher frequencies, and I could use it to go ahead to weld aluminum as well with a 2% thoriated. So there's with a lanthanated. You can do everything with a lanthanated if you know how to sharpen and you know what you're doing. If you can't do it, then there's something wrong in your process. You might have to ask me for more details on this, or contact me for more details if you want to get into this a little bit deeper. So the lanthanated series are the ones that I'm gonna hold close and dear. Ceriated are very common again. I must put in a good word here for thoriated, because it gets a bad reputation. Now, thorium, if you're involved with science at all, you recognize that thorium is radioactive. All those things all those elements on the bottom of the periodic table, all those elements have some form of radioactivity. Thorium happens to be one of them. They've done lots of studies, and every few years they take away all of our thoriated tungstens. And they've done lots of studies and found out the only way to have a problem, the only way to get an exposure to thorium, is to breathe the grinding dust. So my point will always be, if you guys have a place where you sharpen tungstens, you should have ventilation in that area. You should be taking that ventilation and you should have it ducted in such a way that when we sharpen our tungstens and it sucks the dust away while we're welding. And while I'm on this topic, and this is super, super important, we do not use tungsten carbide grinding wheels to sharpen tungstens. These tungstens are not tungsten carbide. There's no carbon in them at all. It's just tungsten. They're not even hard. If you put a sharp point on it, you can put it down on a piece of plate and wear that point off quick because there's no carbon. So keep in mind that these are not hard. Okay? When we're setting current selection, I like to use 1 amp per thou. This is pretty good for constant current power sources. So if you've got a stick electrode that's 1/8 of an inch diameter, your amperage should be starting out at about 125. If you've got a TIG tungsten and it's been sharpened at 332, it's nominally going to be about 94 amps, right? 1/8 125, so it's the decimal equivalent of what we're playing with. Now, sharpening a tungsten, there's a couple of details you need to know, but first I want you to understand the effects of sharpening it. So, look at the angle of these, and it might be different than what you think, so let's be careful here. If I want to make a big wide weld, I put a lot of taper on my tungsten. And I do that because the emanation is at 90 degrees. It actually, and they've actually put a little 90 degrees right in here for us to represent that that's the direction it goes. So we're sending the arc plasma out sideways here to get a wider weld. Hence, if we actually make everything a little bit not as tapered, we get a little bit smaller. But notice as we get smaller, we're getting deeper. Right? We're concentrating heat. This is heat spread out over a larger area. This is heat spread out over a smaller area and depth. This is heat concentrating in one area or a smaller area, so it goes deeper again. And yes, if you're wondering, I've actually taken these and I've blunt them right off to try to get as small as I could. I've taken 1/16 and 332 in the past and just made them blunt. And by blunt, I mean I've just gone straight across and made them flat and give it a little spin. And it gives me the narrowest, of course, the narrowest condition for my weld. Now, sharpening has to be considered as well. Sharpening, because sharpening could cause problems when it comes to styration. This is the grinding wheel leaving marks in it along the edge of this axis. If you try to make these grind marks around, if you try to sharpen it like you're sharpening a pencil on a grinder or something like that, you will make spiral grinding marks on it, and it will cause an unstable arc in this area. It'll cause the arc, because the arc has to come down, it's got to spin around all these different lines, because these lines are very specific gouges. When you have a situation like the one on top, the dispersion is always going to be clean because the grind marks are like that. This is another area that I'll be doing a demonstration when I come to your shop, and we're going to go through how to sharpen it and go through some safety protocols. Plus, I'm always going to want to inspect your area to find out if it's not complying, but if it's dealing with the problems we regularly have with the dust. So you don't want to give anybody, especially from health and safety, any concern, so we'll address it while we're there. I make a quick little point here. I've had a few people go to grind wheel using a grinding wheel like this, and they've actually bumped it and end up pushing it right through their hands. So I always tell people, do not Do not put your hand on the bottom of these. And I will demonstrate how to do this. And I will wear a full shield, a full face shield while I do it, because it's popped up and hit many people in the throat. When it comes to diameters, we already talked about these diameters and what they represent: 187 amps, 125 amps, 94, and 63 amps. It's 1 amp per thousandths of an inch, so it makes it very, very simple. So that's it for this portion. The second portion of this program should be seen as soon as possible. The next portion will actually be P7, and that's where we talk about tool steel and the metallurgical considerations to go along with it. Thank you very much for your time. Please let me know. My contact information is right here. Please let me know if there's anything I can do for you, and if there's any way that I can improve on this. I'd always look forward to hearing from you. Okay, thank you very much.